This is question number 1. So they're saying that a particle B of mass 5 kg is at rest on a smooth horizontal table. Then another particle A of mass 2.5 kg moves on the table with a speed of 6 meters per second and collides directly with B. In the collision, the two particles coalesce. Find the speed of the combined particle after collision. So this is directly a question of the conservation of momentum. Since we have two particles, there is no friction since there is a smooth horizontal table. There are two particles and we are to find the speed after collision. So first let's write the formula in terms of this question. Here I have written the formula for the conservation of momentum, where u is the initial velocity and m is the mass, and AB is the combined particle. So first let's write down what we know. The initial speed of A directly before collision is given to us as 6. So this will be 6, and the mass of A was 2.5, and then we have the initial speed of B, which was 0, so this entire term will become 0, so we don't need to add. And then we have the other side of the equation or the formula. So this AB is the combined particle, and this is the speed we have to find out, which is the speed after collision. And then since both particles coalesce, which just means that they become one, so it will have the mass of both A and B, so that will be 5 plus 2.5 kgs. So if we simplify this, we get this, and dividing 7.5 on both sides, we get that the velocity of the combined particle directly after collision is equals to 2 meters per second. On to part B. We have to find the loss of kinetic energy of the system due to the collision. The key words in this question is kinetic energy, system, and collision. The formula of finding a change in kinetic energy is always half times the mass multiplied by the final velocity squared minus initial velocity squared. However, this formula will not work in this part of the question. Movement is always equals to energy, or more importantly kinetic energy. So first we knew that A was moving towards B on a smooth table and B was not moving at all. So B was at rest, meaning B did not have any initial kinetic energy. However, A did have energy since it was moving, means that it would have had the energy of half times its mass, which was 2.5, and 6 squared, which was its initial speed. That means that the initial energy in the system was 45 joules. Then came the second part, in which A, B collided and they became one particle. And in the first part, we found out the speed directly after collision, which means that the particle moved after collision, so there will be energy. This will be half times the mass, and since it is a combined particle, it will be the masses of both A and B, so 5 plus 2.5, and then the speed directly after collision was 2, so this will be 2 squared, and if we calculate this becomes 15 joules. 45 joules is the initial kinetic energy, and this 15 joules is the final energy in the system. So we need to subtract those to find the loss. So 15 minus 45 is 30. So that means that the total loss of kinetic energy was equals to 15 minus 45, which is equals to 30 joules. On to question number 2, we have that a car of mass 1400 kg is moving along a straight horizontal road against a resistance of magnitude 350 newtons. A. Find in kilowatts the rate at which the engine of the car is working when it is traveling at a constant speed of 20 meters per second. So first let's draw a diagram. So this is the straight horizontal road. Let's say this is the car. It has a mass of 1400, so its weight will be 14,000. And then they're saying that the car is moving along, so the engine of the car is exerting a certain driving force with its power. So there will be a driving force, also known as the forward force. And they have told us that there is a resistance of magnitude 350 newtons, which is basically friction 350, and it will act, let's say in this case, leftwards since the car is moving rightwards. And other than that, they have given us the speed at which it is traveling, which is constant, of 20 meters. So the key word in this question is the rate at which the engine of the car is working, which is just a fancy way of saying power, and in this case instantaneous power, and its formula is always equals to the driving force multiplied by the velocity. So we have the velocity, which is 20, but we need to find out the driving force in order to find the power. We can find out the driving force using the forces formula, which is forward force minus resistive force is equals to mass multiplied by acceleration. Why this works is that the forward force in this case is also the driving force. So we will write this as the driving force. There is a resistive force of 350 newton, which is a friction. And then since the car is moving at a constant speed, the acceleration will be 0. So the right side of the equation will become 0, making the driving force equals to 350. Now we have both the driving force as well as the velocity, and we can insert it into this power formula to find out the rate at which the engine is working. So power will be equals to 350 multiplied by 20, and that is equals to 7000 watts. Now they asked us to give us the answer in kilowatts, so we will divide it by 1000. So that means the power of the engine is 7 kilowatts. For part B, they're saying that find the acceleration of the car when its speed is 20 meters per second and the engine is working at 15 kilowatts. So what they've given us is the power again, which is equals to 15,000 watts, and its speed is 20. Now note, they have told us that this is not the constant speed, so in this case there will be acceleration. In order to find the acceleration of the car, we will need to use the forces formula, which is this, as we know. But for that we will require the forward force. So if you look closely, you will see that we can find out the forward force or the driving force using this information that we have. So power, which is 15,000, is equals to the driving force multiplied by velocity, which in this case is 20. Dividing 20 on both, we get that the driving force is equals to 750. Other than that, the friction will remain the same, which was given to us as 350, as given in the prompt of the question. 750, the driving force minus resistive force of 350, is equal to the mass 1400 times A. This becomes 400 is equals to 1400 times acceleration. Simplify this, acceleration is equals to 400 divided by 14. So this is 400 over 1400. Simplifying this 2 zeros cancel out, leaving 4 over 14. Simplifying it further, we get 2 over 7. This is question number 3. Coplanar forces of magnitudes 8, 12, 10 and p newtons act at a point in the direction shown in the diagram. The system is in equilibrium. Find p and theta. So the condition that they've given us is that the system is in total equilibrium. What that means is that it is in equilibrium both vertically and horizontally. So the criteria for that is that the forces acting upwards must be equal to the forces acting downwards, and the forces acting leftwards must be equal to the forces acting rightwards. So let's resolve these forces. So besides this 12 Newton force, all other forces are acting in a diagonal manner, so we will have to resolve both of their components. For instance, this 8 Newton force, it has a upward component as well as a rightward component. The rightward component will be 8 cos 30, since it is with the angle, reference angle, and the component acting upwards will be 8 sin 30. Similarly, this 10 Newton force will have a leftward component and a downward component. The downward component will be 10 sin 45, and the one acting leftwards will be 10 cos 45. We have this P Newton force, so I will do it with a different color so we can differentiate it from the 10 Newton force components. So it will have a upward component as well as a leftward component. The upward component will be P sine theta, and the leftwards will be P cos theta. So now let's write these forces in terms of these two conditions. So as for the first one, we were talking about the vertical forces. So this P sine theta and 8 sine 30 are acting in the same direction. This will be P sine theta plus 8 sine 30. This must be equal to this downward component force of 10 sine 45. Only in this case will the system be in equilibrium vertically. So first let's simplify this further. So we can take these two like terms on the other side. This means that P sine theta is equals to 3.07. Now let's look at this second criteria, the equilibrium in the horizontal direction. So we have this 12 Newton force acting completely rightwards, as well as this 8 cos 30 which is also acting rightwards, and then the forces acting leftwards is this 10 cos 45 as well as this P cos theta. So this must be equal to P cos theta plus 10 cos 45. And again we can take like terms on both sides. So this 10 cos 45 will take to the other side. P cos theta is equals to 11.587. Now we need to find the value of P and theta. And if you look at these two simplifications that we had, we will see that we have P as the like terms, and we can also see another trigonometric identity, which is that sine theta divided by cos theta is equal to tan theta. So let's say if I write P sine theta divided by P cos theta. So these two P cancels out, and that leaves tan theta, which is equals to, and now we have the values of sine theta and cos theta, which will be 3.07 divided by 11.587. And when we take the tan inverse of this fraction, we will find that theta is equals to 14.5 degrees. Now we can substitute this value of theta in any of these two equations. I will take the one of P sine theta. So let's say P sine 14.5 must be equals to 3.07. So P is equals to 3.07 divided by sine 14.5, which is equals to 12.2 newtons. So we have both the values of theta as well as P. So on to question number 4. They say that a particle P moves in a straight line. It starts from rest at a point O on the line, and at time t seconds after leaving O, it has an acceleration a meters per second, where a is equals to 6t minus 18. Find the distance p moves before it comes to instantaneous rest. So for acceleration, we have 6t minus 18, which basically means that there is variable acceleration, so it keeps changing. Hence, we will also have variable distance as well as velocity. So we know that whenever we integrate acceleration, we get velocity, and when we integrate velocity, we get displacement. And in the case that the velocity is not change signs, as in from negative to positive or positive to negative, the displacement is also always equal to the distance. So first we can do these integrations to find out the equations for both the velocity and the displacement. So first let's integrate the acceleration. So we get the velocity is equals to 6t squared divided by 2 minus 18t plus c. So this is equals to 3t squared minus 18t, and this c will be equal to 0 since this is the y-intercept, and since the reference point is this point O where it starts from, we can say that when t is equals to 0, both the velocity and displacement should also be equal to 0. So if we substitute t is equal to 0, we will find that we will get velocity is also equal to 0. So this arbitrary constant will also be equal to 0. So this is the equation for velocity. Moving on, if we integrate velocity, we will find the equation for displacement, and that will be 3t cubed divided by 3 minus 18t squared divided by 2 plus c. Again, this arbitrary constant is 0 since when t is equals to 0, displacement is also equal to 0. So we get the formula for displacement equals to t cubed minus 9t squared, and that is the equation for displacement. We need to find out the time when the particle is at instantaneous rest. So what we do is that we equate this equation equal to 0, the velocity equation, this over here. So if we simplify this velocity formula, we can get t squared minus 6t since we divide 3, and simplifying it further, we can write t is equals to t minus 6, and equating velocity equal to 0, we can find that t is equals to 0 and t is equals to 6. So these are the two times when the velocity is equals to 0. Now let's make sure that the particle does not change directions, since in that case distance and displacement will be two different things. So we know that the equation for the velocity we found out as 3t squared minus 18t, and that the velocity is equals to 0 when t is equals to 0 and t is equals to 6. And this is a quadratic equation, so it will probably look like this. So when we draw a velocity time graph, we can see that this is velocity and this is time. So this is, let's say this is t is equals to 0 and this is t is equals to 6. So let's take any value between t is equal to 0 and t is equal to 6. Let's say 3. T is equals to 3. We will find that velocity is equal to negative 27, meaning that it will be somewhere over here. So this shows that the particle starts from rest, so it is velocity is equals to 0, and then it gets negative, and then it gets more negative, and then it comes to rest when t is equals to 6. What this negative velocity means is that from the reference point O, let's say that we take the positive direction as the right side and the negative direction as the left side. What it means is that it moves in the opposite direction. So let's say it moves left. What this also indicates is that it keeps moving in a straight line, so distance will be equal to displacement in this case. So what we can do is that we can substitute this t is equals to 0 and t is equals to 6 in the displacement formula directly, and that will equal to distance traveled. So when we put in t is equals to 0, we will find that displacement is also equals to 0. And then when we put in t is equals to 6, we get the displacement equals to negative 108. Again, it means the same thing, that instead of moving rightwards, the particle just moves leftwards as indicated by this velocity time graph that we drew. So now we have the distance traveled between the times when the particle is at instantaneous rest, which is 108 meters. So with that, we're done with question number 4. So on to question number 5. They say that two particles of masses 0.8 kg and 0.2 kg are connected by a light inextensible string that passes over a fixed smooth pulley. The system is released from rest with both particles 0.5 meters above a horizontal floor. The subsequent motion, the 0.2 kg particle does not reach the pulley. For part A, we need to show that the magnitude of the acceleration of the particles is 6 meters per second squared, and we need to find the tension in the string. So in order to find the tension and the acceleration, first we need to be sure of the direction of the tension as well as the direction of motion. So we are given these two particles, And let's resolve the weight first. So this is 0.8 kg, so that means that it will move downwards. There will be a downward force of 8 kg and this will be 2 kg. So we know that 8 is greater than 2. What that means is that this 0.8 kg particle will move downwards while this 0.2 kg particle will move upwards. Now what will be the direction of the tension? So for this 8 kg particle, the tension will be upwards in this direction, and as for this 0.2 kg particle, it will also move upwards. Now since these two particles are connected by the same string, what that means is that they will have the same acceleration, same distance traveled, as well as the same speed. As long as they are connected and there is tension in the string, these three conditions will hold true. Now in order to find the acceleration and the tension, we can use the forces formula, which is forward force minus resistive force is equal to the mass multiplied by the acceleration. Now we will use this forces formula in terms of both the particles. So for the 0.8 kg particle, the forward force will be its weight, which pulls it downwards, which will be 8, and then its resistive force will only be the tension in the string, since the tension in the string is acting in the opposite direction of motion. There is no friction since it is a smooth pulley as mentioned in the question, and then its mass and then its acceleration. As for the 0.2 kg particle, the forward force will be the tension in the string. It helps it move upward, which is the intended direction. So that will be T, the same tension, and then the resistive force will be its weight, which pulls it downwards, so it's 2, and then its mass, and then the acceleration. So these two are simultaneous equations which we can solve. So this plus t and minus t cancel out. 8 minus 2 will be 6, and 0.2 and 0.8 will be equals to 1a. So that proves that acceleration is equals to 6 meters per second square. And then for the tension, we can just substitute this value of a back into any of these two equations. We'll use the second one. So t minus 2, 0.2 times 6. So that means t minus 2 is equals to 1.2, making the tension equals to 3.2 newtons. So with that, we are done with both the tension in the string as well as the acceleration. So for part B, they are now giving us the other part of the journey, which is when the 0.8 kg particle hits the floor. So what that is telling us is that both the 0.8 kg particle and the 0.2 kg particle have now traveled a distance of 0.5 meters. Since they both are connected by the same string, so they'll both travel the same distance. Now we need to find out the greatest height of the 0.2 kg particle above the floor. This is the pulley and this is the floor. So now the 0.8 kg particle is over here and this 0.2 kg particle is now over here. So once this 0.8 kg particle hits the floor, there will be no tension in the string. What that does is that it changes the acceleration and it will not remain the same as it was in the previous part, in part A. Now we need to find out how much this particle travels upwards without there being tension in the string. In order to do that, we need the initial velocity, the final velocity, as well as the acceleration. When the particle reaches the maximum height, what that means is that it stops moving, and that means that the final velocity will be equal to 0. So this needs to be 0. And the other part of the question is the acceleration. So there is no tension. So we can use the forces formula in order to find the acceleration. So the forward force, there is not any. So the resistive force will be the weight of the particle which is pulling it downward, so 2, and then the mass is 0.2 and the acceleration is unknown. Dividing 0.2 on both sides, we get minus 10, which you will also note is the force of gravity. So the particle is moving against the force of gravity, so it will now have an acceleration of -10. Now we have the final velocity, which is 0, the acceleration. What we don't have is initial velocity. As we established in the previous part, we said that as long as both the particles were connected by the string, they will have the same speed, acceleration, and the distance. So the initial velocity of this particle will be the same speed of the other particle when it hits the floor. So now let's look at the initial velocity and how we can find that. Now we will look at the part of the journey before collision. So they said that the entire system was released from rest, making the initial velocity equal to 0, and we found out the acceleration in part A, which was 6. This was when they were connected by a string. The final velocity is unknown, and since the particle hits the floor, we know that the distance is equal to 0.5. So now we can find the initial velocity, or in this case the final velocity, using the v square minus u square is equals to 2ax formula. So the final speed is unknown, and since initial is 0, we won't write that, times 6 times 0.5. So the final speed, this v squared, is equals to 6, making the initial or the final velocity equals to under root 6. So now we have this final velocity, which will become the initial velocity in this part. So the distance the particle travels is unknown. The acceleration we figured out is -10, and the initial velocity is now under root 6, and the final velocity is 0. So 0 squared minus 6 is equals to 2 times -10 times x. So -6 is equals to -20x, and dividing 20 on both sides, we get that 0.3 is equals to x. This is the distance the particle travels after the 0.8 kg particle hits the floor. Let's map the entire journey. So they're asking us for the height above the ground and not the distance that the particle travels. So initially both the particles are 0.5 meters above the ground. So this will be 0.5, and then the particle travels 0.5 meters so that the other particle hits the ground. So that is another 0.5. And then when there is no tension in the string, the particle travels 0.3 meters. So that means that the greatest height above the ground is 1.3 meters. Have that a car of mass 1500 kg is pulling a trailer of mass 750 kg up a straight hill of length 800 meters inclined at an angle of sine inverse 0.08 to the horizontal. The resistances to the motion of the car and the trailer are 400 newtons and 200 newtons respectively. The car and trailer are connected by a light rigid tow bar. The car and trailer have speed 30 meters per second at the bottom of the hill and 20 meters per second at the top of the hill. So for part A, we have to use an energy method to find the constant driving force as the car and trailer travel up the hill. The energy method, a very simple formula that you can always use, is that the total work done by the driving force is always equals to the change in kinetic energy plus the change in potential energy plus the work done against friction. So for this equation, I will be looking at the entire system, meaning the car and the trailer together rather than individually. So for the total work done by the driving force, we know that the car is pulling the trailer up a hill. So the engine of the car is exerting a certain driving force which is unknown. So the total work done also has the formula of driving force multiplied by the distance traveled. And in that case, that is the length of the hill, which is 800 meters. That will be 800. And then we have the change in kinetic energy, which has the formula of half times m multiplied by the squared minus initial velocity squared. And then the change in potential energy is always the mass multiplied by gravity multiplied by the change in height. Work done against friction, that is the force of friction multiplied by the distance traveled. When I say that I will be looking at this entire system for this equation, what that means is that when we're talking about the energies, I will look at the energy that both the car and trailer exert together. So for example, when we're talking about the mass, we will talk about the mass of the car and the trailer. So that will be 750 plus 1500, so that's 2250. And then when we're talking about the force of friction, we will be taking both the friction of both the car and the trailer, so that is 400 and 200, so that will be 600. Driving force multiplied by 800 is equals to half times 2250. And then they've given us the final speed, which was 20 meters per second at the top of the hill, so that will be 20 squared. And then the initial speed was 30, so that will be 30 squared. Potential energy and the work done against friction, I will be doing the workings over here. So for the change in potential energy, we have mgh. So for m, we will be using 2250, and then the force of gravity is 10. Now, in order to find the change in height, we'll have to look at the hill as a right triangle. The hill's length is 800 meters, so that means this hypotenuse will be 800 meters. And they also told us that it is inclined at an angle of sine inverse 0.8. So this angle is sine inverse 0.8. And then this perpendicular will be the change in height. Since it is going from the bottom of the hill, so this is height 1 and then this is height 2. So this perpendicular will be the change in height. So we can use a trigonometric identity in this, so which is sine theta. So theta in this case will be the angle of the hill. Sine, and then for the angle, we know that they've given us the angle as sine inverse 0.8. That means sine of sine inverse 0.08 must be equals to perpendicular, which is the change in height, over the hypotenuse, which is 800, the length of the hill. Now sine of sine inverse just leaves 0.08, so that means that 0.08 must be equal to the change in height over 800. That makes that change in height equals to 800 multiplied by 0.08, which is equals to 64. So that is the change in height, which we can take back into the change in potential energy formula. 2250 times 10 multiplied by 64. That makes the change in potential energy equals to 1440000. And as for the work done against friction, we have the force of friction on both the car and the trailer, 600, multiplied by the distance traveled, which is 800, and that will be equals to 480,000. Now we can use these values in the initial equation which we were writing. To simplify that, again we get the driving force multiplied by 800 is 144, and then plus 480,000, which is the work done against friction, and that simplifies it down further, and 135,500. When dividing 800 on both sides, we get the driving force equals to 1696.875, and if we want to round off, that is 1700 newtons. So that is the driving force exerted by the car. So for part B, they are saying that after reaching the top of the hill, the system consisting of the car and the trailer travels along a straight level road. The driving force of the car's engine is 2400 newtons and the resistances to motion are unchanged. So we need to find the acceleration of the system and the tension in the tow bar. So the new changes that they've given us, that instead of traveling on a inclined hill, now we have a straight level road. Other than that, now they've given us the driving force of the car's engine, which is essentially the driving force of the entire system, since the car is pulling the trailer upwards. So that is 2400 newtons. And other than that, we have the resistances to motion, which are the same. So for the car it was 400, and for the trailer it was 200. So in order to find the acceleration and the tension in the tow bar, we will use the forces formula, which is forward force minus resistive force is equal to the mass multiplied by the acceleration. This is the best option since it includes both the acceleration and the tension in the tow bar. So now when we're using the forces formula, we will not look at the entire system, rather we will look at the objects individually. So for the car, the forward force is the driving force that it exerts. So that will be 2400, and then it will also have a force of friction, which was 400 acting on it, and other than that it will have the tension, and its mass was 1500, and then we have the acceleration. So both the car and the trailer will have the same tension and the same acceleration since they are connected through a tow bar. Since the trailer is behind the car, the tension in the tow bar will act as a driving force for the trailer, and it helps it move forward. So for the trailer, the tension will be the forward force, and the resistive force will be the friction, which we established was 200, and then we have its mass and 750, the acceleration. Two are simultaneous equations, and since we have two like terms, the acceleration and the tension, we can cancel out this plus t and minus t. So this becomes 2400 minus 400, which is 2000, and then subtract it with the further 200, we get 1800, and then 1500 plus 750, we have 2250A. We get acceleration is equals to 0.8. Now substituting this acceleration in the first formula, the car's formula, we can find out the value of tension. So 2400 minus 400 will be 2000, and then minus t, which is the tension, is equals to 1500 times the acceleration, which is 0.8, and we simplify it further. So we get 2000 minus t is equals to 1200, which at the tension in the tow bar is equals to 800 newtons. With that we are done, since we have both the acceleration as well as the tension in the string. For question number 7, they say that 3 points A, B and C lie on a line of greatest slope of a plane inclined at an angle of 30 degrees to the horizontal, with AB is equals to 1 meter and BC is equals to 1 meter as shown in the diagram. A particle of mass 0.2 kg is released from rest at A and slides down the plane. The part of the plane from A to B is smooth. The part of the plane from B to C is rough, with the coefficient of friction mu between the plane and the particle. So for part A, given that mu is equals to under root 3 over 2, find the speed of the particle at C. So for this question, the final goal is to find the speed of the particle at C, and the condition that they've given us is that the part of the plane from A to B is smooth. What that means is that there's no friction from A to B, but they're saying that the plane is rough from B to C. That means there's friction in B to C, and this particle is moving downwards. So first we'll resolve the weight of the particle. We'll have two components. Since the plane is inclined at an angle of 30 degrees, this angle inside will also be 30 degrees. And there will be a downward component of 2, since that is the weight. This will come 2 cos 30. And the component that pulls it downwards will be 2 sin 30. Having no friction means that the acceleration of the particle at AB will be higher and different than BC, since no friction means no resistive force. So this question will be done in two parts, since it is part of one journey from the particle that starts from A and then ends at C. The first part, which is the journey from A to B, what we know is that the distance is 1 meters. So distance is 1. And we know it's released from rest, so the initial speed will be 0. And we are unaware of the final velocity, which will be the velocity at B. And we don't know the acceleration as well. So in order to find the velocity of the particle at B, we need to first find the acceleration. We can do that using the forces formula, which is forward force minus resistive force is equal to the mass multiplied by the acceleration. So the forward force will be this 2 sine 30, and there will be no resistive force since there is no friction in AB, and the mass is 0.2 A. The acceleration will be 2 sine 30 divided by 0.2 leaves 5. So the acceleration is 5 meters per second square. Now we can use this and other information to find out the speed of the particle at B. We will use the v square minus u square is equals to 2ax formula. So the final speed, we don't know, squared minus the initial speed is 0, so we won't write that. 2 multiplied by 5, which is the acceleration, and x, the distance, which is 1. That means v squared is equals to 10, making the velocity of the particle at B equals to under root 10. Now moving on to the second part of the question, which is the movement of the particle from B to C. So for this part again, the distance is again 1 meter as shown in the diagram. The initial speed, which will now be the speed of the particle at B, which we found out is under root 10. The final speed is unknown, as well as the acceleration. First, let's find the acceleration using the forces formula. So the forward force will again be 2 sine 30, and then we will have the friction, which is always equal to mu multiplied by r. So the mu is given us as under root 3 over 2, and the value of r, which is the normal reaction, which is always perpendicular to the plane, is equals to 2 cos 30, since the particle is in equilibrium vertically. This is equals to 0.2 A. When we simplify that, we get that the acceleration from B to C is equals to negative 2.5 meters per second squared. Now we can use this information as well as the distance, which was 1, the initial speed, which was under root 10. Now we can find out the final speed, which is the speed at C. So v squared minus u squared, so this will become 10. 2 times negative 2.5 times 1. So that means v squared is equals to minus 5 plus 10, which is equals to 5. That means that the velocity of the particle at C is equals to under root 5, and if we simplify it further, this is 2.24 meters per second, and this becomes the velocity of the particle at C. For part B, they are saying that given instead that the particle comes to rest at C, find the exact value of mu. So mu is the coefficient of friction, and the condition that they've given us is that the particle comes to rest at C. Other than that, everything remains the same, which means that the speed of the particle at B remains the same, which we found out to be equals to under root 10, as well as the distance of BC, which was 1. We also now have new information, which is that the particle comes to rest at C, which means the final velocity will become 0. Again, we don't have the acceleration, and we don't know the value of friction as well. Since we're talking about the journey from B to C, so there will be a component of friction. So We can use this information in order to find the value of the acceleration. So v squared, which is 0, minus under root 10 squared, which is 10, is equal to 2 multiplied by the acceleration times 1, which is the distance. That means that the acceleration is equals to minus 5 from BC. Now we can use the acceleration, the forward force, to find out the value of friction using the forces formula. So the forward force will be a component of the weight. Just pulling it rightward, so that was 2 sine 30, and minus friction, which was a resistive force, and the mass, which was 0.2, and acceleration, which we found out as minus 5. So 1 minus friction is equals to minus 1. This makes the value of friction equals to 2. So now we can use the value of R as well as the total value of friction to find out the coefficient of friction, since we know that the value of friction is always equals to mu multiplied by R. So 2, which is friction, equals to mu times 2 cos 30, and we know that cos 30 is equals to under root 3 over 2, and if we multiply that by 2, we are left with under root 3. Mu equals to 2 divided by under root 3. And with that, we're done with part B of question number 7.